Hi, everyone. Welcome to the, I don't know what number this session this is, but this is the HLSL and Vulkan There and Back Again. That was our working title, and it made it into the final thing. Apologize if it's a little silly. And there's been a lot of work done in the ecosystem recently as far as HLSL and Vulkan. And if you were at the SIGGRAPH Khronos event, it was just me up there talking about HLSL and Vulkan, but I went and made some friends. And now they're going to present about HLSL and Vulkan as well. And so what we're going to cover is SpearV Opt, and then Matthias is going to cover some how to get from HLSL to Vulkan. And finally, there'll be a deep-ish dive on DXC SPIR-V. And so let's get started. Greg?
Well, I'm Greg Fisher. I'm a compiler engineer from LunarG. And we're going to talk today about using SpearV Opt to shrink your shaders and legalize your shaders, particularly HLSL shaders, when you use them with Vulkan. So the goals of the talk are to answer the following questions here. What is SpearV Opt? And what is the status of SPIR-V size these days? What is HLSL legalization, and why should you be concerned about that, or why should Vulkan programmers with HLSL shaders be concerned about that? And finally, once you are concerned, how to use SpearV Opt to alleviate your concerns. All right. All right, before we talk about SpearV Opt, we should probably, I'll just go over what is SpearV for those that might not be aware. SpearV is the intermediate representation for shaders for Vulkan. It's a binary format. SpearV is to Vulkan like as perhaps DX bytecode is to DirectX. So maybe possibly a way to think about that, and we'll see some other parallels actually as we go over this. So SpearV is a binary format. It's primarily generated from higher level language shaders such as GLSL or HLSL. And they are generated by using several different front ends, GLSL or GLSlang validator, which is part of the GLSlang project Khronos, and that front end has been around for a while and has just recently been adapted to parse HLSL as well, and that generates SpearV. And then kind of new on the scene, the DXC front end, it's a Microsoft, I'll talk a little bit more about that. It's a Microsoft front end for HLSL that's been recently fitted for SpearV. SpearV also has a disassembler and assembler, so you can disassemble, edit, reassemble if you wish. It has a validator to make sure you didn't make any mistakes when you did edit it. All right, so SpearV Opt. This is a part of a project, the SpearV Tools project in the Khronos group on GitHub. It's a collaboration, and it's monitored. Well, I can't think of the word now, but it's essentially Google kind of maintains it. The work that I'm going to talk about today is a collaboration between folks at Google and LunarG with support from Valve, and some other additional significant contributions from folks involved with Mesa and Roblox. Basically, SpearV Opt is really just a collection of transformations, SpearV to SpearV transformations. The ones that I'm going to talk about today are specifically designed to reduce the size of, either reduce the size of your SpearV shader or to legalize it. And I'll talk about what that means in just a few minutes. Basically, in order to reduce the size, well, all of these passes utilize kind of classic platform-independent compiler optimization techniques that have been developed over the last 5, 10, 20 years. So, the first set of these passes was first announced back in August of last year at SIGGRAPH, and have generally been available since then. And since then, actually, there's been quite a bit of additional refactoring, improving additions to it. So it's a pretty active project right now. So reducing size. When I first got involved with this, we were interested in reducing the size of SpearV. It was as it was generated by GL Slang Validator. It was like most front ends. It was generating fairly raw, fairly inefficient code, I guess you would say. And so the idea was to apply a number of classic optimizations to reduce its size. Here's just a list of some of the more prominent ones. If either these are designed to reduce, to eliminate code from the shader, or it does analysis or enables analysis to do additional removal of code. Recent measurements are showing us around now about 10%, within 10% of DX bytecode size. So we're pretty happy with that. We feel so we're fairly close. For some games with quite a number of shaders, the original size of SpearV had been fairly large and almost prohibitive in some cases. So the idea of getting these down to DX bytecode in that neighborhood was something that was considered desirable. Now, now onto the term legalization. It sort of got coined as part of in the last few months. What we came across was that there were some constructs in HLSL that are not directly supported by graphics hardware and was not supported by Vulkan. So however, we determined that using standard code transformation techniques, we could transform the shader code into a form that could be directly executed on graphics hardware. So let's see. Right. So and this was this is not a problem that's peculiar only to Vulkan and to our front ends. As a matter of fact, FXC, if you're from, likely you know, everybody here in this room knows what FXC is. The Microsoft shader compiler also is a highly optimizing and transforming compiler. And so it basically does the same thing. And so, as a matter of fact, FXC actually, well, the current graphics hardware and drivers rely on the fact that there are a number of optimizations and transformations that FXC performs before the shaders actually get to the driver. So, therefore, we also in our ecosystem, in our tool chain, we also then needed to do those same transformations in our optimizer, hence essentially in SpearV Opt. So we are, one of the kind of goals, ongoing goals, is to get SpearV Opt to be equivalent to the optimization strength of FXC. I'm going to give just a couple examples of some some structures that in HLSL that do require transformation. GL slang validator when it compiles HLSL, if it finds one of these structures or one of these, it will actually even evoke a message saying that legalization is required. These constructs, again, are optimized away through variations of function call inlining, dead code, dead flow elimination, value propagation, dead code elimination. One of the structures is one of the constructs is structures that contain opaque types, samplers, textures. So here's an example of that. And this pattern is fairly common in different shaders where a sampler or texture is assigned into a structure. That structure is passed maybe to a function call here, and then the sample is executed using values out of the structure. Well, that's so this structure is really not. It's not supported by Vulkan. It's considered quote unquote illegal by Vulkan, even though it's expressible in SpearV. So we needed to optimize this away. And so these values are propagated using standard compiler techniques, and voila, the red code's gone. And we end up with just a single sample operation at the point of the original call using the actual texture and sampler value. Another structure that we take care of in SpearV Opt is local structured buffers. Here's an example where this is kind of a simplistic example, but the pattern is holds out in a number of shaders out in the wild, where you have a global structured buffer declared, but then inside of a function or inside of main, you've got a local structured buffer that's declared and then assigned the value of the global buffer, and then the local object is referenced. So again, we use compiler techniques to transform that just into a reference of the global object. One last example, and this is of using SpearV Opt. This is not as much maybe a legalization as it is a way of avoiding validation layer errors that we were seeing with a particular shader. In these shaders, we had both we had dead references to textures, samplers, and or buffers, and the calling application knew that these were dead, and so they weren't binding these objects. However, the validation layer would throw an error. It would say, you've got these dead references to these objects, or well, it would say you have these references to these objects, but they're not bound by the outer application. So, however, after pre-processing the shader, the SpearV Opt was able to remove these dead references. So here's just an example again. Again, a fairly simplistic example here. We've got both a live texture sample using text 0 and a dead reference of text 1, and SpearV Opt would remove the 1. So how do you, so SpearV Opt can be called directly if you, on a SpearV file. There is a command line option just to legalize for legalization of HLSL and those operations. It's also an option to optimize for size. And we also have the ability to call individual passes and to specify the order, and you can call them in any order that you wish. And those are all documented. And we also, SpearV Opt also has an API interface, and it has methods then for calling kind of a predetermined set of legalization and size reduction passes. And as was mentioned earlier, I think in a previous talk, SpearV Opt can also be called through indirectly through the front end. So, however, and this is kind of one of the points of the talk, is that due to legacy reasons, the GL slang validator front end does not require SpearV tools and SpearV Opt to be linked in when you build it. So it's up to the user to make sure that it's linked in if they're indeed compiling HLSL for Vulkan, or at least compiling any such shaders that might have legalization issues. If indeed SpearV tools is linked in with GL slang validator, legalization will be called by default on HLSL shaders, and size optimization is available optionally. And with the new DXC front end, which I think people will be talking about here just in a little bit, we do have default legalization and optimization already, and those can be disabled. And also the GLSLC wrapper for GL slang validator and SpearV tools also does legalization by default and has an option for size reduction. All right, and some of the folks that have contributed directly to SpearV Opt or its integration with the front end. So now I will now introduce Matthias.
So thanks, Rick. And I'm Matthias. I'm the other side of support at amd.com if you send questions about Vulkan and the shader compiler. And I'm going to talk a bit about how to get from HLSL to Vulkan, because that's the main thing we've seen when people are trying to port to Vulkan. They have huge code bases in HLSL and they want to figure out how to run them. So let's get started. So where are we currently? So as I just said, huge HLSL libraries, and you want to use them with Vulkan, and Vulkan only accepts SpearV, right? There's no HLSL path into it. At the beginning, a couple of people have tried the macros way, so I just hash define everything and then pass it into GL slang, which I would certainly advise not to try like in practice for shipping games. It becomes very unwieldy and there's no real reason why you should be doing this. It's more like a stopgap measure. The other thing is what a couple of people have tried is like you translate source to source. So you write your own HLSL parser and then you do magic. It usually ends at the stage where you write your own HLSL parser. So as Hai will testify, writing your HLSL parser is quite some effort, so you shouldn't be doing this. This also includes stuff where you translate like HLSL bytecode into GLSL and then try to compile it again and so on. That's just losing so much information along the way. And I will be showing you a slide why you shouldn't be doing this. So the thing I want to focus on are the two middle parts, right? So you have HLSL, a large code base, and you just use a compiler which natively accepts HLSL, which is GL slang or DXC. And now all of you would hope, of course, okay, so I just replace like copy GLSlang C to fxc exe, and then I just compile everything as usual and then be done, and then my talk is over. But unfortunately, it's not quite that simple, but it's getting reasonably close at least. So the problems are, we have the main problem we have is actually a different binding model between D3.11 and 12, and then to Vulkan again, right? So D3.11, that's like slots and named bindings, and D3.12 has this root signature thingy, and then it has descriptor heaps, which are typed, which Vulkan doesn't have, and basically like what it boils down to is, so on the left-hand side, you can see like the HLSL way of doing things. So you have a root signature, which links to descriptor heaps, and that's the API side. So you have two levels of indirection on the API side. But on the shader side, you're only writing like register T0. And in the Vulkan world, you have two levels of indirection on the code side because you have the set and binding thing. But at the same time, you only have one level of indirection on the API side. And that's where all the nice, we just pretend everything is the same, basically starts falling apart. So we need to just like link both worlds somehow. And that's not the only problem we have, right? So in GLSL versus HLSL, we have some resource types which don't really map. Sometimes it's just naming things which confuses people, like why is an image a UAV and why do I need a structured storage buffer for things? And some things have just no equivalent. So you can't have a read-only structured buffer because it's always read-writable from the API side. At the same time, you can have it read-only in the shader, and that's just making people's life unnecessarily hard because they want to map the whole stack, and they just have to like, don't do it here, but do it over there. As we saw in Greg's talk about legalization, like some things are opaque objects you can't pass around, even though you can express it in SpearV. Once you try it, you will notice that it might work in certain circumstances when the compiler actually figures out it looks like fxc and I can just do it, but sometimes it just breaks. Bindless is very different, so I think Hai will be covering bindless in a bit, mentioning it at least, yes. So that's going to be very, very different. I'm not going to cover it here because we have only 1 hour of talking time. And as far as I can tell from experience with a couple of games so far, it's like the descriptor remapping is the main issue where people try to like subdivide ranges and do all of sorts of crazy stuff. So I'm not going to solve it here, and I can't give you a solution which will work for all of your engines as much as I wish I would be able to. The message I want to give you here is that's something you need to be aware, right? If you want to support both D3 and Vulkan, or you're porting from D3 to Vulkan, that's the area where you need to like set aside some time, think through it, look what works for your engine, and that get working. The good news is here, like all of the tools you need are in there because like everyone has his favorite binding way, and all of them are supported by the tools by now. And there is some stuff, if you only port HLSL, you will notice it's just missing in Vulkan. If you're just porting HLSL, you will notice that in Vulkan there is some functionality you can't access from HLSL at all, like push constants and input attachment and specialization constants and so on, which require you to mark up your HLSL in a special way to be able to use those functionality. That's mostly interesting for those people who plan on shipping the same code base for some platform which is D3 based and some platform which is Vulkan based. And we have seen this in the practice, right? So people have like one HLSL code base, they still want to use those Vulkan specific features, so they need to mark it up somehow. And again, there's good news here. We have extended HLSL in a way which makes it easy to integrate all of the special binding stuff you need for Vulkan without breaking HLSL completely. In fact, the only problem you have with all of this stuff is you need to have a define which then just gets no opt for fxc, and things will just work. So you can have the same code, it's like all fxc code, all HLSL which fxc accepts, and you only need to add stuff to make it like all working for Vulkan. There is no special, like you don't need to specialize twice, right? You only need to specialize once. So there's no if HLSL blah, else if Vulkan blah, and yeah. So that's the key point here, right? So all of your HLSL code base, like on day one, you can at least compile it for Vulkan. It will not exactly work because you have some stuff missing, but you can incrementally add all of this and you can take advantage of the new features. And like, from my point of view, that's going to be where you're going to spend the majority of your time when you try to actually port stuff over, and it's like annotating these things. Usually you will want to like don't do this by hand, right? You will just have some tool which produces bindings and so on and so forth. But again, good news, everything is in place. This works today. The same syntax works on DXC and GLSlang, so you just type it in, you can run it, and it works, and there's like no magic required here. SpearV Opt, yeah, so we've covered this before. I'm going to cover it again because it's such an important thing. So my claim here will be, so if there's the one thing you take away from here, which is HLSL is awesome, and that's why Vulkan uses it. So the other thing you should be taking away is, if you have a compilation pipeline, it should be ending in SpearV Opt before you pass it into the driver. The one thing is it's required to be legal SpearV anyway, so you have no much way around it. But at the same time, it does optimizations, and those optimizations which reduce the output size. So anything which makes your SpearV smaller after you have run it through the optimizer is generally a safe assumption that this will make your SpearV run faster. And if it doesn't make your SpearV run faster, it will at least make your compile time faster, so you will save time when the game loads up for the first time. So there is like no excuse to not use SpearV Opt, right? You should be always using it. There are some notes I would like to. Please prefer unroll and don't unroll yourself. Like, don't force unroll things. So we have seen horrible shaders coming in where it's like my SpearV is 2 megabytes because I unroll all the things. And turning on all options is also not a good idea. Like, we have seen some people who are just like SpearV Opt, and then there's help, and then it just dumps all the options, and then we just grab that back in, and then turns out not so much. And the SpearV Opt thing, you should also use it if you compile GLSL, right? So there's no reason why you should only use it for HLSL, you should only use it for GLSL. The net result is you will get usually significant things in terms of like size of your shaders, so there should be in the ballpark of DX bytecode. If that's not enough, you can compress it further. There is domain-specific compression tools available. Aros is unfortunate in the GDC this year, but he's written a tool called SmallV, and that solves one of the biggest issue with SpearV, where everything is 32-bit and all the identifiers are 32-bit, even for your own use, like 4 bits out of them. So that should get you on the shipping code base size roughly to D3D or below, hopefully. So if not, then we should probably work on this and talk to us, but it seems pretty okay. Like, nobody has been complaining that they can't fit the shaders on a Blu-ray anymore, which was the case when they started porting. And performance, everyone's favorite topic. So now we assume we have everything ported, our game is shipping, we have the download is done, we press the start game button, and then everything just runs 10 times slower, which some developers used to call the Vulkan tax, because it's like once you have gone through all those layers of compilers and things have happened, and what came out at the end was not as performant as it used to be. In particular, because GLSlang and DXC compile in a very literal way. This is my syntax tree, and this is my output. And if you try to decompile your output, you will notice you can reconstruct your whole syntax tree. And if any one of you has ever compiled C++, this is not how optimizing compilers work. So there's some stuff you still need to be on the lookout, but the major Vulkan text items are basically gone. So the stuff where I would be on the lookout is the stuff where GLSlang and DXC tend to generate what I would call interesting code. It's usually very easy to spot. So anything where around arrays, especially like temporal and local, temporary arrays, local arrays, constant arrays, anything you would think that is like, this is getting created once up front and then initialized, might be actually created every time for every single loop iteration up front and then get initialized every single time you actually need it. So what happens is, like, in your innermost, tightest loop, you're looking up an array of 10 items, and SpearV will allocate a new one and then store 10 values into it every single time, and then the loop unroller decides to unroll this, and then you have a shader which is 1 million times initializing an array, because all of them are unique and different. That's being improved a lot. It's just some things which have, FXC never did this, and the compilers have never seen this, so they might sometimes get confused. Also function calls, GLSL is still getting confused about function calls occasionally. If you pass in some structures, it will just give up on types, which is also getting rapidly better, and it's not really a problem in practice anymore, but there's still some stuff where the SpearV has function calls when you compile it, and If the compiler sees function calls, they might occasionally generate funky code, because I don't think any one of you has used the D3D11 class linkage stuff and so on. Did anyone try ever this? Okay, that's the only time FXC was generating function calls, and a lot of crying was combined with this. And also you have to be on the lookout when sometimes annotations don't get translated correctly. So you pass in like unroll, and then after you have mangled it through 3 different compilers and 4 different optimizers, your unroll might have not made it through the final SpearV. That's something you should be on the lookout. But overall, I would say we are very, very close. If the SpearV is really slower, then you try the tools, and you just try as many SpearV Opt options until it becomes fast enough. If it doesn't, then I have more good news for you, because we have tools you can actually inspect the whole pipeline through. And here's some motivating screenshots. You can hopefully at least guess which tool this is. Does anyone know this tool? Okay, 5 out of 150. That's Balder will be very sad. So this is RenderDoc, and what you can probably only read from the first few rows is this is HLSL in RenderDoc in a Vulkan application. The Vulkan application apparently is called Dota 2. And you can press a button here, and then you can see the SpearV. And then you press another button, and you can see like our intermediate presentation, and then you can see even ISA. And that should allow you to optimize shaders pretty quickly, or at least spot the worst offenders. Because you can see immediately, okay, I have HLSL, I have the SpearV, I have the ISA, and if they don't match, or semantically they become very different, then probably something is going on. And that's exactly the same comfort you have today in RenderDoc with HLSL and D3D. It's just HLSL in Vulkan. And that's also one of the reasons you shouldn't be like mangling your HLSL into something else and then getting it into Vulkan, because why? Here you can just pass an HLSL and just, it's all the same, right? And even better, if you have the same game running on both D3D and Vulkan, you can just open up 2 copies next to each other, and then you just go like, HLSL is the same, DirectX bytecode versus SpearV, okay, there are similarities, and you go ISA is very different, and you give me a call. Or your other favorite IHV vendor. So to sum this up, where are we? So games are shipping on Vulkan, and they have HLSL source. So you can go on Steam, and you will find some applications which have Vulkan rendering based on HLSL. Single HLSL source works. So you can keep all your HLSL source. You don't have to rewrite it. And going forward, you will be able to use DXC to just like, ease the burden on all of this porting. And before I finish this, like one thing I would encourage all of you to do is now, because you have SpearV, you could consider using SpearV as your internal company intermediate representation, because SpearV is very valuable for this. You have high-level information in there. You have a stable code base, and it's a well-defined API. And you might consider just generating all your shaders and store them as SpearV internally, or write tools around SpearV, because I think that will enable a lot of people to just have more fun with shaders again, instead of being stuck with like this, I have my HLSL textual everything. And getting from SpearV into other shading languages is actually pretty simple, right? So that might be something you would want to look at, right? So most people just look at SpearV as just something like, okay, I have this thing given by Khronos I need to use to get my shaders into Vulkan, but that's not it, right? You're getting a well-specified intermediate representation useful for other things, and I've seen at least a couple of people experimenting with, I compile my own stuff to SpearV and have a lot of fun with it. And that's it from my side, and next up is Hai.
Thank you, Matthias. All right, so we're going to take a look, sorry, let me introduce myself first. My name is Hai Nguyen. I work with David Netto on DXC, on the SpearV project specifically. And we're going to take a look at some of the work that's been done on DXC and some of the things that are applicable to workflows and some of the collaboration that we've been doing with GL Slang. So let's get started. Sorry, I need to move a mouse out of the way here. Okay. So here's an overview of what we're going to chat about. The first is just a brief history of how DXC got started. David covered a lot of this in his talk already, so I won't go into excruciating detail. The next part is how we broke down the development process into compilation, legalization, and optimizations. They just happen to coincide with how the build process takes place. And after that, we're going to look at some of the what's here now and like SM60 wave ops, semantics, reflection. And after that, we're going to look at what's coming. And lastly, DXC is not a small project, and it took a lot of community effort. And I'd like to show some appreciation for all the blood, sweat, and tears I've been through with this. Okay, so the project was started in early 2017, initiated by David Netto. Google met with the Microsoft DXC team, and it was very positive. And so, I think we began coding pretty much immediately. HLSL has the recognition of being a language without a spec, and it's even it's cunning enough to get past even the experts. And I was talking to Baldor recently, and I was asking him about the usage of the uniform keyword, and when I gave him the example, the first response I got back was, "I did not know that was legal." And so Microsoft plans to evolve HLSL rapidly once DXC is stable, and this, of course, presents a particularly interesting challenge for us if we wanted to keep up. So when you can't keep up, just join them. So leverage the front-end parser. And so that brings us to where we are today. SpearV at Google contributes and maintains the SpearV backend for DXC. It's open source under the LLVM license, and it's hosted on GitHub. SpearV also leans on, or initially leaned a lot on GL-Slang's progress to get started. In the early days, the code gen was identical to GL-Slang, and as we progressed, things began to diverge a little bit, but they both generate code that work. And these days, both projects work in collaboration to maintain parity between the HLSL functionality. SpearV also works very closely with the SpearV tools team. In fact, they sit right next to each other. And DXC SpearV leans heavily on SpearV Opt for optimization and legalization. We also do a fair bit of outreach to the community and to the IHVs. Some of them may not like me right now. To get feedback on how to shape DXC going forward, because ultimately we want this to be a very successful product for the Vulkan ecosystem. So in the development, we broke down how we wanted to achieve getting to the end product, what will look like the 1.0 product for DXC SpearV. We started out by breaking into 3 high-level goals: compilation, legalization, and optimization. Compilation is the parsing of HLSL to the generalized SPIR-V. We call this the front-end process, and it happens within the DXC codebase. Next up is legalization, and it's the transforming of generalized SPIR-V to the Vulkan dialect. We refer to this as the back-end process. And Greg's talk went into a lot of detail about this, so I'll skip over that. And lastly, optimization is also a back-end process. It transforms the Vulkan SPIR-V to be more performant. And as Matthias alluded to, there are some controversial transforms like loop unrolling. We've been having this kind of this debate between ISVs and IHVs about if this is productive or not. So we're going to settle the score once and for all at SIGGRAPH 2018. So come there to see some benchmarks. So SpearV has been really busy. Lei Chang and Asan Nassiri are the 2 main contributors to SpearV. As you noticed, they're the 1 and 3, first and third major contributors to the DXC project. So to just kind of pull the curtain back a little bit about legalization, we are aware that there are some generated SPIR-V that is problematic for consumption. A lot of it has to do with the complex HLSL opaque object referencing. It's structs containing structs containing structs containing more structs that contain opaque objects. And if you don't believe me, I've seen the production code, and I'm sure you've seen the production code that does this. So we are aware of these things, and this is the first time legalization has been attempted for HLSL and Vulkan, so we've learned a lot of valuable lessons, and we're working with the IHVs to address this as quickly as possible. And these fixes will come, or the resolution will come in bug fixes at DXC as well as driver updates. Okay, going on to a little bit more positive things. So what's here today? So we have full SM 5.1 support, bugs and features that Vulkan can't support notwithstanding. If you do find a bug in anything related to SM5, SM5.1, please report on the GitHub. And if we're missing anything, I know that ROVs are missing right now, but there's not a direct way to address that in Vulkan, so we're still working on that. SM60 wave ops came in with Vulkan 1.1. Sorry, I forgot to delete a note there. Some other highlights of DXC that have made into DXC recently. Global variables are now collected under the global C buffer, and these are variables that are externally visible and are of simple types like int or float2 or matrix, not any of the opaque objects. We've also been experimenting with what it looks like to get extensions in HLSL from the DXC side, and we implemented SPV KHR draw shader parameters as a first version of this. And there's a bit of magic that's happening in here. When you use the IDs from this, it automatically detects it and then inserts the extension. The two most exciting things that have happened in our little local team is that we've got semantics and counter buffers in as an extension, and we'll talk about in just a little bit. We're adding the Vulkan extension, or we'll be proposing the Vulkan extension soon to support this on the driver side. And lastly, we've been doing a little bit of work with reflection because there's been a lot of community feedback about reflection, and we wanted to provide a lighter path for reflection. So let's take a look at semantics and counter buffers. So the DXC team, along with GL Slang, worked on two extensions to make this happen. In order to decorate for semantics, we needed a decoration, or we needed an opcode that permitted a decoration to a variable or to a struct member that could carry a string. And so opt decorate string Google and opt member decorate string Google were added. And once we had those, we could add decorations the decorations themselves. The first one we added was HLSL semantic. It's out of order here. And this leverages the previous extension to add the string decoration to a variable or a struct member for the semantic that is defined in the HLSL source. And the other one is, this has been a problem for quite a while, and there's been a lot of workarounds, but there is a decoration that explicitly links a structured buffer with the counter buffer that is associated with it. And this is a hard link. You don't have to go and parse the name of the variable anymore with @count. The Vulkan extension is in progress. Both of these are opt-in features for the compilers. To opt in for DXC, you do -f SPV reflect. And to opt in for GL Slang, you do -HSL functionality 1. I believe GLSLC supports -HSL functionality 1 too, right? Tomorrow, okay, tomorrow. So here's a bit of the semantics and counter buffers in action. On the left side is the source code, and you can see my workflow there. And this is what it looks like in the SpearV. So it's working, it's there. There is, however, one slight catch to this. Because the drivers can't consume the opcodes and decorations yet, they need to be stripped before they get fed to the driver. But we thought about this, and what we're going to do is we'll provide a code snippet that you can use. It's about 20 lines of code that Lei Chang wrote, and it'll take out all the opcodes for the decorations for semantics and counter buffers, and you can pass the SpearV clean to the driver. This code will appear in the SpearV reflect repo. All right, so what is SpearV reflect? SpearV reflect is a small C library. It's two files, one header, one source. Court Stratton and myself have been working on it. If you start using it, send all bugs and request to Court. This is what it looks like. He's right over there. And this is the data that it reflects, vertex attribute locations, basic type information associated with that. Court pointed out recently that it only assumes everything is 32-bit. So if you're trying to build a vertex input from that, you need to make sure that you correct it for whatever format that you're using. It does a pretty extensive reflection of descriptor bindings and sets, uniform storage, push constant blocks, relative offsets, absolute offsets, raw size, etc. And it also does the HLSL resource types. So there's literally an ID field in the struct that tells you if it's a CBV, SRV, UAV, or sampler. And we went through a lot of pain to make this happen because it's not obvious how to derive that from the SpearV. And of course, it will contain semantics and counter buffers. So here's an example of what the reflection looks like from our test harness. As you can see, it's parsing through pretty much everything that cbuffer.spv contains. So one little note, it says source language unknown here. We just merged the pull request to add the language version to DXC. It's a little embarrassing, I apologize. And here's a more crazy version of a test harness that does all the SRV, UAV, et cetera. One of the ones that was kind of controversial in this one was the one that people can't seem to get correctly is the storage versus textile buffer. These are actually images, and they kept on getting parsed as buffers. And so this will go live on my personal GitHub repo. It'll go live on the 23rd, and if you find any issues, please file them on GitHub, and Court will get to them. Court also loves issues, and this is what he looks like again. That's his Twitter pic, by the way. So you have references. And we're working to get this into SpearV tools, and when it does go into SpearV tools, SpearV Reflect will likely get deprecated. So here's a few things that are coming soon that I think are pretty exciting. The first up is descriptor indexing, and this will enable bind lists on Vulkan, and it will also enable non-uniform resource index. I hope you're excited about this feature because everybody I talk to about HL, this is the first thing they ask, and I'm really excited about it just to not get asked about it anymore. The IHVs have confirmed that they are supporting this, but we don't have a date on it, so it's coming soon. Extension support into DXC. It will likely come as a command line option. It'll be -f SPV extension equals extension A, and then the same thing, extension B, et cetera. It's to keep in conformance with the Clang format. And of course, more things for shader model 6, 64-bit integers, 16-bit scalars, barycentrics. And here's a few things that we have talked about and debated internally and argued about, but we haven't come to any firm conclusions yet. But people have asked for them. The first one is inline cbuffer initialization. This is a little bit difficult to do because we have to package data in the SpearV file itself. So we're still talking about that. You might see an extension called HLSL functionality 2 or 3 that adds this. And I'm sorry, this was supposed to be root signatures, not root descriptors. I've just been thinking about root descriptors a lot lately. One of the features that DX12 has is that you can slam a root signature directly into the HLSL source, and this has been raised several times. So we want to try to explore what this means. And also, GLSL has this nice ability for you to specify a extension inside the source itself. We've been thinking about that too. It'll probably come in the form of a syntax that looks similar to how you specify the bindings currently. Before I wrap up, I want to say one last thing. If you are using DXC and you have a pretty extensive code base, we are aware that some of the legalization can take a little bit of a long time. There's a man in the audience here that's heading up this, solving this particular problem. I won't embarrass him. No, I'm kidding. And DXC is by no means a small project, and it took a lot of people to get DXC to where it is today. And we still have a long ways to go, but it's a community effort, and it really shows how much interest there is in Vulkan, and when Vulkan moves forward, everybody moves forward. So the DXC team itself is myself and Lei Chang and Aslan Desiri at Google, and David heads it up. The guidance is David Netto and John Kesnich. Every time we get into a debate that we can't solve, we email John or David, sometimes very late at night. SpearV Opt, Greg Fisher, Diego Novillo, Steve Perrin, and Alan Baker have been working hard to getting all the legalization and performance optimizations in. And we've had a lot of our friends from the IHVs that we bother pretty much constantly about getting things done or getting our stuff corrected for their driver. And the Khronos members that have really helped push this effort forward. The legalization stuff actually started as a conversation between Dan Ginsberg and myself on pretty much the first time we met. And then that kicked off the entire workflow of how I got started. Neil Henning has provided a lot of input onto SpearV, how SpearV is restructured in the code gen. And Tobias Hector has given us a lot of feedback on how things should flow in Vulkan itself when SpearV is executed. And Dan Baker, I'm not sure if he's here today, but Dan Baker was one of the original authors of FXC, and he's had to put up with a lot of direct conversations about why did you do this? And here's the list of companies that have contributed to the progress of this work. And so at this time, I'd like to invite Matthias and Greg Fisher back up for any questions the audience may have. We've got 5 minutes. 5 minutes.
Well, I have a question.
If you don't have a question, I'm just going to start reading SpearV Opt codes to you.
All right. Greg, during your talk, you mentioned that GL Slang Validator did not require inclusion of SpearV tools. But now what if I use the GL Slang Validator from the LunarG Vulkan SDK?
Greg, you can take that one.
Excellent.
Yes, happily. If you use GL Slang Validator out of the LunarG Vulkan SDK, it does have SpearV tools linked in, and so legalization will be done by default.
And please use the ones from the SDK, because then we have the version number and we don't have to compile it ourselves.
Yeah, one question. You said that you are going to have like similar optimizations than DXC, but DXC has a lot of stupid optimizations as well, like from the old VEC4 architectures in DirectX 11 era, that it does some extra optimizations because that was fast back then, but it's not anymore with scalar architectures. Are you going to just ignore those things, or like the legacy stuff that is on the DXC?
I can take it.
So you might be surprised, but we actually talk with those guys here, and if they do stuff which is completely stupid, and we tell them about it and ask them to not do it.
Yeah, okay, that's good.
For a friendlier version of the answer, we are quite aware of some of the differences of how FXC structured the optimizations versus how we have to structure the optimizations these days. And we are at a slightly different place because of how DXC is choosing to, or how DXC DXIL is choosing to go about optimization. And you know, we want to optimize for things that make sense on modern hardware and going back as far as it makes sense. But we don't have any recipes. We haven't settled any particular recipes right now. And when we do, we'll document them.
Yeah, I was actually talking about the older FXC that is still used in most projects, and the newer one might be better than this, obviously.
I mean, so the good news is none of those optimizations which would make things worse have gone on in yet, and I don't expect this to happen actually.
Okay, that's nice to hear. So you don't need to like revert those optimizations in drivers anymore.
Yeah. Cool. One more question. So you can take one more.
Okay, this assumes that everybody is all right with HLSL and is happy with it.
We're done. Yay.
Awesome. Well, thank you, everybody. It's been a pleasure talking to you guys.